All right, today we're going to start section 4.1. It's about divisibility. As with most of the material that we do, we're going to start with some definitions so that we make sure that we're all using the words in the same way. And before we do that, let's take a look at our leading idea. So the concept of divisibility reveals patterns of order, harmony, and structure within mathematics, qualities that reflect the intentional design of a faithful creator. Exploring how numbers divide evenly into one another, because that is what we're going to mean by divides, is it goes in evenly, invites us to appreciate the consistency and balance woven into creation. Integrating faith in God with the study of divisibility encourages a thoughtful and purposeful approach to teaching, helping learners recognize the beauty and reliability found in the world around them. Let's pray. Dear Heavenly Father, I thank you for these students. I thank you for the break that we just had. I thank you for an opportunity to continue to learn and to grow. I pray that as we start this new unit of material, that we would be open to receiving what you have for us, that you would give me clarity in my examples and give the students good questions to ask to gain clarity as well. We pray in Jesus' name. Amen. Okay, so as the leading idea mentioned, this word divides has to do with this sort of idea of being even, and we're still working in the whole numbers, all right? So we're not talking about anything negative. We're not talking about any fractions and decimals. It's not like that. So if A and D are whole numbers, then D divides A, and it's written with this vertical bar, okay? D, that vertical bar is sort of like the word divides, like a division bar, but it's not, okay? And then A, if and only if there is a unique whole number Q such that A is equal to DQ. If D divides A, then D is a factor or a divisor of A, and A is a multiple of D. That's a lot. Just jot it down, and I'll give you an example, and you'll be like, oh yeah, that makes sense, okay? But just jot it down first. Okay, you ready for an example so that we can kind of put some pieces here together and see what this is saying? Okay, so this says 2 divides 6. Does 2 divide 6? Does 2 divide 6? Yes, the answer is yes. Can you do 6 divided by 2? Yes, you can, right? This means 2 is on the outside, 6 is underneath, and it goes in evenly. Okay, that's what it's telling you in like this new bar notation. Okay, 2 divides 6. And what it's telling you with a Q is that the reason for that is because there's such a number Q, it's 3 in this case, where the 6 is equal to 3 times 2. Okay, there exists a number, it's another whole number, it's the number 3, so that when I multiply 2 by that number 3, I get back 6. That's what it means to divide something. We actually call this number at the beginning, right, this 2, which is here and here, a divisor or a factor, okay? And likewise, this number 6 that's happening here, we call a multiple. Multiple can also be thought of as it comes sort of from like the multiplication tables, right? Like if I wrote down the 2's multiplication tables, 2, 4, 6, 6 is going to be in the list. It's a multiplication factor or a multiplication piece after you get the 2's, like when you're all the 2's down. So that's what that looks like. Okay, is that okay? You do this, and you've done this for years. You just haven't had quite the same terminology with this word divides in this notation. That's the only difference right now, is this notation. Okay, so we're going to use this notation over and over again. Theorem 4.1 actually extends this idea and says, for any whole numbers A and D, if D divides A, and n is any whole number, then D divides NA. And I'm going to show you again with that same, we're going to keep running through that same example of why this works. Okay, so 2 divides 6, we all agreed, right? Yes, yes, okay, good, well agreed. What that means is that I can take this number 6 and I can multiply it by anything I want. Whole numbers still, okay? We're not going anywhere else, always whole numbers in this class, okay? When we get to chapter 5, we'll get into integers, which is some negatives, but still working whole numbers right now. I can multiply this number by any other whole number. And let's do an example. Let's say we do the number 5. It's random, okay? So if I multiply that 6 by 5, I would get 30, agreed? 6 by 5 is 30. Whatever that number had been, I chose 5. 2 is going to divide that as well. Okay? And that should make sense, because if I break the number 6 down, it's got a 2 in it. It doesn't go away when it gets multiplied by something else. I just, tack on more multiplication to it. It doesn't lose, in this case, its evenness. If it was even and it gets multiplied by something, it's still even. So this is actually a fact about divisibility. Okay, we've got a series of 5 facts coming up. Y'all ready? This talks about addition and subtraction. So if you have whole numbers A, B, and D, the first one here says that D is going to divide the A and the B. And I'll give you an example. Actually, I think let's do this. Let me let you write them all down first. And I'm just going to be quiet so you can kind of just not listen to me, back and forth with your screen, and then I'll explain the details, okay? You do get finished, if you just set your pencil down so I can kind of keep track of who's still writing, that would be helpful to me. The first one and the third one, they start out the same, right? Telling you there's some divisibility of some things going on. And then the only difference between them, well, there's a couple of differences. This one tells you that A has to be bigger than B. That's fine. That doesn't really matter that much. But the difference is whether or not they're adding numbers together in the result over here or whether they're subtracting, right? That's the difference in those two. So let's actually look at both of those two with the example I started with, where 2 divides 6. So 2 divides 6 in both cases. And I need that same 2 to divide something else. So I want you to give me an example. What's another number that 2 divides? 8. And I think, let me actually do this. Let me do the 2 divides 8 first and then the 2 divides 6, just because that will be in the right order for the second one so that the first value is bigger than the second one. And if it's not, you just switch it, it doesn't matter. Okay, so I've got the number 2. It divides a couple other even numbers. The first statement says that if I take the 8 and the 6 and I add them together, 2 is going to divide that as well. Now I'm using specifically evens because it's easy for us to think about that, maybe easier anyway, than some of the other things I could use. If I add 2 even numbers together, I get an even number, right? Of course I do. And that would work for any multiple. If I add 2 multiples of 3, I get another multiple of 3. Okay? So there's nothing special about the 2. It's just easy for us to process through that because it's small, really, because 2s are small. And it's also true in the third one that if I subtract them, this is going to happen. So as long as the reason they want the first one to be bigger is because when they subtract, they want to keep it as a whole number. It's actually true if it's reversed as well. We just aren't talking about negatives, right? It's the hush-hush subject right now. Don't talk about them. But it works, okay? So this is saying that if I subtract 8 and 6, right? If I subtract 2 even numbers, do I get another even number? Yeah, I do. I still get an even number, okay? So if I have divisibility for 2 numbers, right? This is my 8 and my 6 here. If the divisibility exists, the divisibility will exist for their sum and their difference. Makes sense. Okay, the other 3 actually have very similar statements at the beginning as well. Not exactly identical, but similar. This one and this one are exactly the same, right? It says the first one divides, right? D divides A, but the second one doesn't. Okay, on the third one, it's the same thing. They just switched it around, right? We've worked with commutativity quite a bit. So you switch it around, it doesn't actually change the result. It just ends up allowing you to make sure that you end up getting positive values when you're subtracting. That's what's going on here, okay? So as we're taking a look at this, these 3 statements are all really pretty much the same. So we're going to start again with the same one that we had before. 2 divides, and I'll use 6 because that's one we had before. 2 divides 6. And in this case, 2 divides 6, it's just in the second spot, okay? And then I need another number that 2 doesn't divide. And let's make it bigger than 6 for the moment so that when I put it down here later, everything will be okay, all right? So tell me a number 2 does not divide. Bigger than 6. 7. Thank you. That was really helpful, Kira. My kids are this all the time. Only word. Okay, 7 would be fine. Let's make it a little bit bigger just because I want it to be a 1. It looks a little bit funny for things to show up as 1s and 0s sometime. So 13, sure, that'll be great. Okay, so let's do 13. 2 does not divide 13. So notice I didn't actually define that, but when we slash something, it means does not, right? We do it with equals and not equals and stuff like that. It works here as well. And so here 2 does not divide 13. And here 2 does not divide 13, like that. I may need to switch an example out, but let me just start with the one I've got so far. Let's look at this first one. So 2 divides 6, 2 does not divide 13. True? True statement to start with, okay? And then if I add 6 and 13 together, in other words, I add an even and I add an odd, what am I going to get? It's going to be an odd, and 2 is not going to divide that either, right? So if I fail on one of these counts, right, if one of these doesn't work, then I'm actually going to end up in a situation where, in this case, the sum does not work either. Okay? The same thing happens down here. Let me actually jump to the bottom one because it's actually set up properly, and we're gonna have to change some on the fourth one. But this bottom one is set up well. The 2 does not divide the 13, right? 2 does divide the 6. I'm putting it only in that order because that way it allows me to keep a positive number. And if I do 13 minus 6, that is I do odd minus even. What happens when I do odd minus even? Still get an odd, right? In this case, it is the number 7. 13 minus 6 is 7. And so we end up having that 2 does not divide 13 minus 6. Let me go back up here and just change this 13 to a smaller number than 6, just so my numbers stay positive. Let's just do it with, how about we do it with a 3? Are you good with that? So 2 divides 6, but 2 does not divide 3. We'll just change our 13 to a 3. Again, the only reason is because it'll keep our numbers positive. And the same thing happens if I do, in this case, right, so the bottom one was odd, 13 minus even gives me an odd, but I can do it with an even minus an odd, and I still get an odd, right? You join evens and odds together, and they create odds when you're looking at addition or subtraction. So these do not divide as well. Do you notice what's not included here? In the conditions. One condition says that divides both, right? That was 1 and 4. 1 and 3, excuse me, the yellow ones. And then the other condition, 2, 4, and 5, right, the green ones, all had it's even in one case, it's odd in the other. It divides one and doesn't divide the other. What's missing?
Both of them not dividing?
Both of them not dividing. That's what's missing. Do you guys see that? And there's a good reason that that's missing, because these can all be stated absolutes. They're all concrete, and they always work all the time. If it divides them both, it's going to divide their sum. If it divides them both, it's going to divide their difference. If it divides one and not the other, it's not going to divide the sum. And if it divides the other and not the one, it's not going to divide the difference, right? Like the sums and the differences, it's always going to work. The problem is that if you have it not dividing both of them, sometimes it works and sometimes it doesn't. Okay? That's why it's not here, is because there's the ability for that to happen in both cases. So let me give you an example real quick. Evens is a really good example to show that it actually would work. So let's say, for instance, we had 2 does not divide 3 and 2 does not divide 13, numbers that you guys gave me just a moment ago. What happens when I add 3 and 13? You get 16. Does 2 divide 16?
Yeah.
It does. So it does not divide, and it does divide the sum. And it would divide the difference as well. As long as I did it in the right order to keep them positive, 13 minus 3, it would be 10, and it would work. Y'all with me? In the case of evens, it actually would do this all the time. And the reason is because it's either even or it's odd. There's nothing in between. There's no middle ground, okay? So when we take a look at this and we do it with another value, so let's do 5s because they're easy to look at as well. Let's say 5 does not divide 12. And 5 does not divide 7. That's true, correct? Okay, but what's 12 plus 7? What's 12 plus 7?
19.
It'll be 19. Is 5 going to divide 19? No. What's 12 minus 7? 5. Is 5 going to divide 5?
Yeah.
Yeah. So it divided the difference, but it didn't divide the sum. Right? So we do have the ability for it to divide both pieces, to not divide both pieces and have either results happening at the end. And that's why they're not on this list. Okay, so what we're shifting to next is to actually look at specific divisibility rules for numbers that you know and love. And we're starting with 2. So these 3 are actually grouped all together on purpose because their divisibility properties are all very similar. So these are the tests for divisibility, or the rules for divisibility, or the properties for divisibility. I don't care what word you use. It's going to mean the same thing on all of them. So the first one's divisibility test for 2. A whole number is divisible by 2 if and only if its units digit is even. Okay? So when you look at a number and you know that the number is even, you really only have to look at one value, the last one. Correct? So if I give you a number, 5,237,427, all you care about is the number 7 at the very end. And that's what this is saying. I just have to look at the last number. If the last number is divisible by 2, it works. And 5 works the same way. If I want to know if something's divisible by 5, I don't know what number I just gave you, but whatever it was, it ended in 7, right? All I have to do is look at the 7. And if the 7's divisible by 5, which it's not, right? But if it is, then it's going to be divisible by 5. The whole value is. And we can do the same thing if it's divisible for divisibility by 10s. We look at the last value. If the last value is a 0, that's all we have to look at. If the last value is a 0, it's going to divide by 10. If it's not a 0, it doesn't. So these 3 tests all have to do with looking at the very last value in the number. Okay, that's why they're grouped together. Does that make sense? The reality is this works for 2 and 5 and 10, but it doesn't work for anything else. I can't do this with 3s. and I can't do this with 7s, and I can't do this with, anything else. There's other divisibility rules that work, but these 3 work like this. Okay, you ready to look at another set? 4 and 8, these are grouped together on purpose as well. And we can actually throw the number 2 in here a little bit, which I'll mention in a second, but 4 and 8 are very specific. In order to decide if a number is divisible by 4, instead of looking at just the last digit, like we did for 2s, 5s, and 10s, we look at the last 2 digits as a 2-digit number. So if it ends in 34, if it ends in 27, if it ends in 16, whatever those last 2 digits are, we consider that as a 2-digit number. And if it's divisible by 4, then the original number, no matter how big and ugly it is also going to be divisible by 4. Okay, so with 2s, 5s, and 10s, we looked at the last digit. With 4s, we look at the last 2 digits. And then with 8s, we actually look at the last 3 digits. This becomes less useful as we go because you don't know most of your multiplication tables of 8 to 3 digits long. But think for a minute if you wanted to. Did not happen to have your phone with you, which would be a highly unusual circumstance at this point, but just pretend. If you wanted to know if something was divisible by 8 and you only had to divide the last 3 digits as a 3-digit number instead of maybe 7 or 8 digits, it would still be easier. Truth? So this is our divisibility rule for 8s. We take the last 3 digits, we look at the last 3 digits as a 3-digit number, we ask, do the last 3 digits as a 3-digit number divide by 8? If they do, the entire number divides by 8. So there is a reason why this is happening in terms of, I'm going to look at 2s, 4s, and 8s for a minute. 2s, we looked at 1 digit at the end. 4s, we looked at 2 digits at the end, and 8s, we looked at 3 digits at the end. Okay, so why is it happening that I'm looking at 1 or 2 or 3? Because it's the powers of 2. So consider for a moment, I'm not asking you this later, but I want you to see that this is why this is happening. If I did 2 to the 1, 2 squared, and 2 cubed, 2 to the 1 is 2, right? 2 squared is 4, and 2 cubed is 8. This is the 4, the 8, and the 2 that we're talking about. The powers tells you how many digits you need in order to know if it's divisible. And why does that happen? Well, because this is divisibility by 8, and 8 is 2 times 2 times 2. There's 3 2s. So I need a 3-digit number. That's why it's happening. It's not really a mystery, but that's what's going on behind the scenes. Okay, 4s and 8s. Do you think we're okay? We're going to practice all of these. I just want to make sure we understand them right now. Okay, the next ones I think 3 and 9. I very, very specifically remember learning this property for 3s. I was in high school, and I think I was my senior year of high school, and it came up, and it was one of those moments where you were like, how did I not know that? This is cool, okay? So in order to know if a number is divisible by 3, we add all the individual numbers in it up, okay? So if it's a 7-digit number, we add those 7 digits together. If it's a 3-digit number, we add those 3 digits together. Whatever it is, we add them up. And if the sum divides by 3, then the original number would as well. This is the first one that maybe should feel like it's a little bit odd. Why would that work? But the cool thing is, not only does it work for 3s, it works for 9s as well. So once you've added all those digits up, you can quickly decide, does it divide by 3 and 9 at the same time? Because the number itself is typically at that point a 2-digit number. Almost always you're going to end up with a 2-digit number. It's going to be in the multiplication facts that you've hopefully still got in your memory from when you learned the multiplication tables for 3s and 9s. Okay? People sometimes get this confused. This doesn't work for 4. I can't add the numbers up and ask, does it divide by 4? I can't add the numbers up and ask if it divides by 7. It only works for 3 and 9. It doesn't work for anything else. Okay, so this is a category unto itself. I add values together. That's for 3s and 9s. Okay, our last set don't really go together. They're just on the same slide. Okay? The divisibility test for 11, I'm going to let you write it down. It sounds super awkward, and it's really not hard to do, but there's really no good way to write it. A whole number is divisible by 11 if and only if the sum of the digits in the places of even powers of 10 minus the sum of the digits in the places of odd powers of 10 is divisible by 11. Allie, that sounds terrible, doesn't it? I can see it all over your face. It sounds terrible to me reading it. Write it down. A divisibility test for 6 is very straightforward, though. It says that a number is divisible by 6 if and only if it's divisible by 2 and 3. And that kind of feels intuitive, because 2 times 3 is 6. Thank you so much. I was waiting. Yes. 2 times 3 is 6. But as intuitive as that last one feels, it doesn't work for all products of numbers either. So we do need to look at why that works in a moment. But first I want to give you an example of the divisibility for 11 so you can see what it's saying. Okay? So we're going to make up a number. I don't even think I have one written down, but we're going to make one up. I'm just going to put it at the top. Okay. Got 34,261,849. The more digits I have, the easier it is to just show you what it's doing. Okay, so I want you to circle every other digit. I'm going to start with 3, so I'm going to circle 3, 2, 1, and 4. Okay, everybody good with that so far? Okay, everything you circled, let's find what the sum is. What is 3 plus 2 plus 1 plus 4? Going once, going twice. 10. 10's what I got. Okay, let me change colors. Let's circle or underline. I'll underline the others that I didn't do. So I have 4, 6, 8, and 9. And I'm going to do the same thing for that one. I'm going to find the sum of 4, 6, 8, and 9. Okay, so I need to add 4 plus 6. That's 10. And then would you get 27? 27. Fantastic. Okay, is everybody good so far? Okay, so this whole idea of even and odd powers of 10 is telling you you're doing it every other one. That's what it's telling you. Some of those places are powers of 10 that are 10 to the first, 10 to the third, 10 to the fifth, 10 to the seventh. And some of them are places that are even powers of 10, 10 to the second, 10 to the fourth, 10 to the sixth, and so on, okay? So you add these together, the two different pieces, and then you subtract them. And really, it's just big minus small, right? There's nothing special about the subtraction. 27 minus 10. What's 27 minus 10? 17. If this number 17, if it divides by 11, then the original number did. If it doesn't, then it doesn't. So does this number divide by 11? No, it doesn't work. 17 does not divide by 11, so 34,261,849 won't either. It's not a hard one to do, but it's a really awkward one to write. Okay, everybody good so far? Okay, so what I want to do is I want to actually look at a particular number, and we're going to go through and look at all of these rules. We're going to come back to this whole business about 6 that I mentioned, alluded to just a moment ago, and talk about the when and whys it works in a second. But let's just practice all these divisibility rules for a particular number. The number we're going to do this with is 24,015. Okay? And we're just going to go through, and they've got a list of them here, 2, 3, 5, 6, 8, 9, and 10, and 11. Those are all the rules we have. And we're just going to make a decision, yeses or no. And I'm going to write them down with a little bit of justification next to each of them of why it works or why it doesn't. Okay? So we're going to start with the number 2. Does 24,015, 15, does it divide by 2? No. How do you know?
It doesn't end in even.
Yep, it does not end in an even. And when you get to the homework, it's not even going to ask you to justify, which means that you can grab your calculator and do it, but I'm promising you if you do that, you're going to miss the point of practicing what we're looking at. And you're going to find yourself struggling to remember how it works if you haven't practiced it, okay? So whether you choose to write it down like I just did, or whether you simply remember, I absolutely need to practice these properties, I don't care. but you do need to practice them, okay? Because I would ask you, if I asked this question on the test, I would make you justify it. Y'all know that, right? Explain is my favorite word, right? It is. I like you to explain things. I want to know what you're thinking. Okay, let's try the next one. 3. Does it divide by 3? Okay, how do you know? Okay, so you're looking at it in a way that works on this one, but wouldn't necessarily work in general. So what's the property for 3s?
You add them all up and if it's divisible.
There you go. So we're gonna,
Equals 12.
yeah, 2, 4, I'll write in 0 just for the sake of writing it, and then 1 and 5. 2 plus 4 plus 0 plus 1 plus 5 is 12. Okay? Does 12 divide by 3? Yes. So I'm going to practice that property, or that notation. 3 divides 12, like this. So since 3 divides 12, 3 is going to divide 24,015. Now Madison noticed something else on this one that is absolutely a true statement. 3 does divide 24 at the beginning, and 3 does divide 15 at the end. That happens to work here. But I could literally have the 2, 4, 0, 1, and 5 and switch the order all up, and it would still work. And it wouldn't be as obvious or as clear that it did, right? So there are going to be cases where you might look at it and know it from another perspective too, and that's not wrong. It's just not as general, okay? How about the number 4? No. How do you know?
Last 2 digits.
So the last 2 digits, which are a 15, right? 4 does not divide 15. Right, above, I didn't write it, but 2 does not divide 5 back on our number, the number 2. 2 didn't divide 5. 4 doesn't divide 15, so it's not going to be divisible by 4. How about 5? Yes, how do we know?
Ends in a 5.
It ends in a 5. It ends in a 5. You could also say that the 5, the number of 5 I'm trying to divide by, divides 5. Right? That's why it works. 5 divides 5. It ends in a 5. Very good. How about 6? We briefly went past that, but we did do it. It's the last one we did. Okay, Tessa, you say no. Why?
Because 2 doesn't work.
Yeah. So what has to work for this to be a property?
2 and 3.
2 and 3. So the reason that this doesn't work is because it does not divide by 2. It does divide by 3, but that's not enough. It doesn't divide by 2. The next one is an 8.
Why don't we have a rule for 7?
There's not a property for 7, unfortunately. If you were to try to divide by 7, you'd simply have to do the division. Yeah, it's a good question. Not one for 7s. What about 8? Does 8 work? Nope, it doesn't. Why not?
15.
Yeah, the last 3 digits, which I purposely made the example small enough for us to be able to visibly see. It's 0, 1, 5, right? That's the last 3 digits. And 8 does not divide 0, 1, 5. Now, it's probably worth pointing out that if the original number didn't divide by 2, there's no way it can divide by 6 or 8 or 10 or 12 or 14 or 16 or 18 or 20. It can't divide by an even because it wasn't even to start with. So you kind of get all those for free if it doesn't divide by 2 anyway. But we're analyzing these with properties specifically to just sort of point out how this works. All right, 9. It's a no. Why not?
This product isn't divisible by 9.
Yeah, so we had the product at the top, number 3, for divisibility by 3. 2, 4, 0, 1, and 5, and it equaled 12, right? That was our sum. And while 3 divided 12, 9 doesn't. So it dividing by 3 is not enough to know that it divides by 9. There's more that's necessary, and it doesn't actually divide by 9. How about 10? No. Besides the fact that it's even, and I told you it's not going to divide by any evens, in terms of the properties, why is it not going to divide by 10?
Doesn't it end with a 0?
Yeah, so the last digit is not a 0. That's what I've got to look for. It's not a 0, so it's not going to work. And then our last one, 11, which remember 11 feels awkward, but I'm going to write this down. So we had 2, 4, 0, 1, 5. So we're going to circle every other one. 2, 0, and 5 add to what? 7. And 4 and 1 add to 5. And if I subtract these, just so that I get a positive, right? 7 minus 5, I get 2. What does it tell me?
Not divisible by 1.
Not going to work, and the reason is because 11 does not divide 2. I'm looking at this value at the end, this subtracted value, this difference, and if 11 doesn't divide it, then it's just not going to work. Okay, so we are going to push pause for a second, because what I want to do right now is something that's not directly on your notes. I want us to establish what's so special about 6 that allows this to work. And we're going to do this in a very specific way. So how many do I have here today? 3, 6, 9, 12. Ooh, groups of 3. That's fantastic. Do you see that? I practiced divisibility just like that. Okay, so I'm going to have, let's do this. Kira, you join over here, and then Emily Kate, you join over there, okay? And then let's do you 3 here, and then Kinley, if you'll come up kind of and join Allie and Emma to get 3. So I want you guys to shift around, get to where you can kind of be in a group for a second. And what I'm going to do is I'm going to create a list. The list I'm going to create is a list of works and doesn't work, examples and non-examples, okay? So this property for 6 is not special to 6 only, but it also doesn't work for everything. There are some numbers that you can do this with, and there are some numbers that you can't. And what I want us to explore for the next 7 minutes is see if we can figure out what the pattern is on the numbers that work that fails for the numbers that don't. Do you understand what I'm describing? Okay, so let's see if I have a slide that's got space on it. This will work. So we're going to do it right here, and I'll erase it when I'm done. So we're going to do examples on the left, and we're going to do non-examples, things that don't work on the right. Okay? So we already have one example. 6 breaks down into 2 and 3, and it works. If it's divisible by 2 and 3, it will also be divisible by 6. Okay, that one works. 8 breaks down into 2 and 4, and it doesn't work. There are numbers that are divisible by 2 and 4 that are not divisible by 8, because you guys just see what I'm describing, right? I'm breaking them down, and I'm breaking them down in such a way that sometimes the breakdown actually works, and everything that works in the breakdown is going to make it divisible by that number, and sometimes it doesn't. Okay, so like how do I know for the 2 and the 4 that they don't work? Well, 4 divides 12. 2 divides 12. 8 does not divide 12. Y'all with me? Okay, so that's why it's a non-example. So I'm going to create a list, and this is me off the fly. I'm just going to write them all down. And I want you to discuss and see if you can find a pattern within your group of the things or ways in which the examples are alike that fail for the non-examples. Okay? So we're going to do one. Do one more of each of them. Okay. All ideas are welcome in your group. So I want you to talk with one another and see if you can find a pattern that explains why these numbers on the left work and these numbers on the right fail. Okay, let's hear some of the thoughts. I mean, I can hear you guys because you're the closest to me. And Kira was on the right track, but examining something that is unintentionally showing up. I heard her say it looks like this list of examples has an even and an odd in each one of them, but you can have two odds. That's okay. What do you think? What do you notice? Somebody said something about multiples. Remember what you said?
I was saying that like on the non-examples, they're multiples of each other, but then it didn't work with 4 and 6.
Yeah. So Kira's right. If they are multiples of each other, it's not going to work, right? 2 and 4, 2 and 6, 3 and 6, 5 and 5. They are, one of them is a multiple of the other, right? Like one of them flat out is multiplied by something and you get the other one, right? But then you see the last non-example, and then 4 and 6 don't work, and neither one's a multiple of the other one down there, right? But that's really close to still being what you're looking for. What do 4 and 6 have in common?
Both divisible.
Say it.
2.
2. They both are divisible by 2. Does that work for everything else in your list?
Not 5.
Okay, they're not both divisible by 2, but what do you see?
They're both divisible by 5.
On 5 and 5, they're both divisible by 5. So instead of specifically saying 2, what if we say they're both divisible by something? Something that's not 1, right? Every number in this list on the far right-hand side has 2 numbers that have a common factor. They're both divisible by something. But look at the list that's in the examples. Doesn't happen, right? Every single one of those pairs, 2 and 3, 3 and 4, 2 and 9, 2 and 5, 3 and 8, 3 and 5. When you take that pair of numbers, the biggest number that divides both of them is 1. And that's exactly why it works. If you have the ability to break the number down, like the composite number at the beginning, this big number down into factors that have nothing in common, we're going to give that a name later, but if they break down into factors that have nothing in common, then you can test those 2 factors to make a decision about the composite number at the beginning. If there's not a way to break it down, or if you break it down in such a way that they do have things in common, it won't guarantee that. There will be numbers that will not work if this is your list that you're trying for. So 6 works because 2 and 3 have nothing factor-wise in common but 1. Does that make sense? There's one other way to describe it, so let me describe it really quick because we haven't gotten there yet. But the other way you can describe it is that the least common multiple of the 2 numbers is their product. So the least common multiple, which we haven't done yet, I know, but the least common multiple of 3 and 4 is 12. But the least common multiple of 2 and 6 is not 12, it's 6. The least common multiple of 4 and 6 down here is not 24, it's 12. So that's another way to describe it. I think that's a little bit harder to grasp personally, so that's not how I think about it, but I've had students think about it that way before. Thank you for bearing with me. You guys are great. Have a wonderful rest of your day. We will table this until Wednesday, which we'll finish it, and it won't be due until Friday. And I'll do that in Canvas once it's open again, okay?